Hello everyone, and welcome to AISC Night School. This is Night School 7, Stability Design of Steel Structures, and this is Session 2, Modern Methods of Structural Analysis, Part 2. As was the case with last week, this week's presenter is Dr. Ronald D. Zemian. Today is February 2nd, 2015. My name is Brent Liu, and I am with AISC, and I'll be moderating this evening's presentation. I want to introduce this evening's speaker, Ronald D. Zemian. He is a professor at Bucknell University. He received those bachelor's, master's, and PhD degrees all from Cornell University. In addition to authoring papers on design and analysis of steel and aluminum structures, Dr. Zemian is the co-author of the textbook Matrix Structural Analysis, and is the editor for the 6th edition of the Guide to Stability Design Criteria for Metal Structures. He was the former chair of SSRC, which is the Structural Stability Research Council, and he's a member of AISC's Committee on Specification, where he chairs the Task Committee 10 on frame stability. He also serves on the AISI in the Aluminum Association Specification Committees and is active with the Steel Joist Institute. Dr. Zemian was awarded with the ASCE Norman Medal for his paper on employed advanced methods in inelastic analysis in the limit states design of steel structures, and he also received the AISC Special Achievement Award and the ASCE Shortridge Hardesty Award for his contributions to the profession related to stability analysis and design of metal structures. Ron, I'm going to hand things over to you. Thanks for being here, and I'll let you take it from here.
All right. Well, thanks, Brent. And good evening, ladies and gentlemen, from a very cold Bucknell University campus. Again, it is great for the Structural Stability Research Council to be joining AISC and delivering this night school course. And it is awesome to have 8 lectures to cover system stability, which is a topic that is so essential to the design of steel structures. As I said last week, Don and I have decided to focus on this subject through the lens of an engineer who has access to modern methods of structural analysis. So here are the session topics for our 8 lectures. And tonight, I'll be continuing through where I left off last week, but this week we'll be focusing on material and second-order nonlinear analysis methods. Next week we'll be having a look at some resources that you can apply these nonlinear analysis methods. And then we'll hand it over to Don, and Don's going to have a look at applying all of this in the actual design, factoring in the direct analysis method. And then finally, I'll come back later in the course and have a look at how we can even go all out and use inelastic analysis to design steel structures. I showed this slide last week, and it's kind of a good place to start, primarily not because the title's there, but because over on the right is something important that happened in 2005. And it was at that time that for the first time in the AISC specification, the word analysis started to appear within the body of the specification. And so AISC began to recognize that more and more structural engineers are weighing more and more heavily on the use of structural analysis, especially when it comes to structural stability. And so now they're starting to recognize, and have been recognizing since 2005, this opportunity. So some key points from last lecture. The first, what I did was review the direct stiffness method. So this was in the second half of that lecture. The first half was all on the direct analysis method. But the second one was really trying to answer the question, how does the computer get the answer? And so like I said, I reviewed this direct stiffness method. It was basically 3 steps. One, equations of equilibrium are formulated. Then we sort of do a translation. We take the internal forces and using stiffness relationships, rewrite those internal forces in terms of displacements. Once we have now a set of equilibrium equations that are in terms of displacements, we can apply compatibility, which simply means the displaced ends of the member of connected members have to displace together, or if the end of the member is connected to a foundation, it won't move, or whatever the prescribed amount of movement is. But once we apply that compatibility, Bob's your uncle, we've taken this large system of equations and we've reduced it to the number of equations equaling the number of unknowns, and then we solve for displacements. Once we have those displacements, we can go back to what I'm calling here a translator. We can get the element end forces, and once we have those element end forces, we can further apply equilibrium and get the reactions. Now, a key part of what I was trying to emphasize in the last lecture was the response of the structure with respect to the computer analysis can only be controlled via the stiffness of the members. All right, so that's our only way of getting in there and accounting for whatever type of effect we're looking for, is to change the stiffness of the members. So again, I was showing an image last week of what you see on your computer, and what the computer actually sees, and then what the computer is actually seeing is a system of connected springs. So if you want to modify something or account for whatever second-order effects or whatever it is you're looking for, the only way into that world is to modify the stiffness of members. I did have an opportunity to go through a first-order elastic stiffness and what that meant. And for these members, we looked at axial force members and flexural members. And two key properties, we can divide them into material property, and there it was the material stiffness, or the modulus elasticity. And with respect to the geometric properties, we're talking about the cross-sectional area, the moment of inertia, and of course the length of the member. But also very important to the stiffness of that member is its orientation. And so we'll be tracking, all right, when we go nonlinear, what happens to these stiffness terms. So indeed, it is time now to go nonlinear. I think, at least from a teaching standpoint, strangely enough, it's easier to begin with the material nonlinear than the second order. So we'll start material nonlinear, and then we'll go into our second order elastic, and then we'll combine the two, and we'll get the full enchilada of second order inelastic. Probably always the best place to start when you talk about material nonlinear analysis is all the way back to that sophomore level strength of materials course you took, where you did a laboratory and you did a tension test. And on that, during that tension test, you stretched the member and you plotted the strain stress relationship. And early on, you saw, especially with structural steels, the material is nice and happy and elastic, and that's where you got your modulus elasticity. But eventually, what would happen is you'll get some yielding. And so now we've reached the yield point of the material. After some pretty significant amount of straining, you actually experience, or the material experience, some strain hardening, brings us up to ultimate and eventually to fracture. Now, one of the things that we do on the computer analysis side, and even really within the specification, is we assume that the material is elastic, perfectly plastic. And so what this means is that when the stresses in the member are below yield, the member is fully elastic, and we're using the full E. Once it yields, we don't try to take into account a strain hardening modulus or anything like that. We simply take the E value and we drill it to 0. So it has either full stiffness, the material does, or no stiffness if that particular material has yielded. Now we're talking about normal stresses. It's important to note that for most structural steel members, when the length to depth ratio exceeds 10, which is almost always the case, then the elastic and the inelastic behavior is being controlled by normal stresses, and these normal stresses are acting in the same direction or in parallel to the length axis of the member. All right. So in most cases, the shear stresses are not impacting the material response of the member. These normal stresses, what can they be produced by? Well, certainly axial force, so they're just taking your traditional P over A. Certainly normal stresses are being produced by bending, both major and minor axis flexure, so there's your MC over I. And then most likely what's happening is you have beam columns, members that are being subject to both axial force and bending. So here it would be a kind of a combination of axial force and bending effects, or P over A plus MC over I. Now there is one more contributor to the normal stress along the length of the member, and it typically comes in the form of torsion through what we might call warping stresses. That won't be discussed tonight, but certainly something, just to have in the back of your mind. If you do have a significant amount of torsion, you're going to pick up some additional normal stresses due to warping, cross-sectional warping. Now, like I was showing in the previous slide, we will assume the material as elastic, perfectly plastic, and almost all analysis done of a steel structure make this assumption. Now, last week I was showing you some slides in which we looked at sort of this. I was trying to get you thinking about spring stiffness and axial stiffness. Well, here we're looking at the same thing, but this time what I'm going to have a look at is the response right through yielding. All right, so we start with a structural member on the right, an axial force member, and on the left we're going to be plotting the amount the member stretches versus the amount of axial force in the member. So we put on some axial force, and the member stretches by some amount delta. And over on the left, we can see the spring stiffness of this little system. And the spring stiffness is basically what you learned your sophomore year in college. It's EA over L. All right? But I think you realize that we haven't yielded anything. And if we keep putting on more and more axial force, eventually we're going to get to the point in which we will fully yield the cross-section. So at this point, the cross-section from bottom to top has fully, the stresses in it have reached yield. And we have reached what we call the yield limit of the member, if you will, P sub y. And P sub y can be calculated simply by taking the yield stress of the material and multiplying it by a cross-sectional area. Now, realizing that the material is now fully yielded through the full depth of the member, none of the material in the member has any stiffness left. It's lost all its elastic stiffness. The E value, like I said, has been drilled to 0. So if we try to put on any additional loads, what we would have is a significant amount of deflections. All right? Now this concept is important. It's very simple. We've fully yielded the member, but I wanted to use this to sort of introduce the first thought on what a plastic hinge is. All right? So this is a plastic hinge being produced by only axial force, and it occurs when the axial force in the member reaches its yield force, or P sub y. Or another way of saying that, and we're actually going to use this terminology, is to take the axial force of the member and divide it by P sub y. And again, P sub y is A times the yield stress of the area times the yield stress of the material. And when that ratio equals 1, then we'll have a plastic hinge. So you can almost imagine now if a computer program was doing the analysis of a truss in which you had all axial force members, it would be watching this ratio of axial force divided by the yield, and when it equals 1, then it would put in a plastic hinge. Now the same concept is true for flexure. All right. So now what we're going to do is subject this thing to some bending. And so up on the right here, you can see I'm subjecting it to some moment, and monitoring on the left the moment on the vertical axis and the amount of rotation at that end where I'm applying the moment as theta. And at first I put on the moment and I get a rotation, and everything remains elastic. So on the lower right of your slide, what I'm doing is plotting the stress distribution. And here is our typical MC over I calculation. And you can see that the stresses are less than yield. And we've got the full member behaving. And the stiffness for this particular example would be 4 EI over L. But if we keep putting on more moment, eventually what's going to happen is the stresses at the top and bottom of the member at the extreme points, the MC over I is going to equal yield. All right, so it's at that point we're going to get some yielding, and once the section starts to yield, over on our moment rotation diagram, we're going to see a loss in stiffness. So you can see now I've put on some additional moment, and what's happened is the stress has sort of started to follow through and is coming from the top down and from the bottom up, and it's all reaching yield as it's being shown in blue here. And that area that's yielded has a modulus elasticity of 0, and the area that's remaining unyielded in red still has a 29,000 KSI material modulus. So what that means, though, is over on the left, we don't have as much moment of inertia, or EI, effective stiffness, as we did before, and so we've lost stiffness, and this member's starting to, lose stiffness, like I said. But eventually, we'll keep putting on more moment, and we'll eventually fully yield the top and bottom flanges. And this is a real knockout punch to this section, because now all that's left in resisting bending is the web, and we don't have a lot of EI left. Again, all the yielded area that you can see here has no material stiffness. If we keep going, eventually what will happen is we'll fully yield the cross-section, and we'll have what's called a plastic hinge here. All right, so you can see we've gone to full yielding through the cross-section. This occurs when the moment equals the plastic section modulus times the yield strength, or when the moment equals m sub p. Now, if we are looking at this with respect to a computer program, what we often do is neglect that in-between, or that partial yielding. All right, we're trying to do analysis of big structures, and we're not going to care about the in-between stage. So in a plastic hinge type of model, what we'll assume is that the cross-section is either fully elastic, or once, in this case, due to bending, it reaches m sub p, it's fully plastic, and at that point we would form a plastic hinge. So again, a plastic hinge will occur when the moment equals mp, or when the ratio of the applied moment divided by m sub p equals 1. Now, one of the things I just want to point out is I'm going to show you a very simple sort of nonlinear analysis, with a material nonlinear analysis. It's used quite heavily, and it does a great job. But it's probably the simplest of all the models you could use. It's often called a concentrated plasticity model, because we're only looking at one specific point. We're not modeling the yielding along the length of the member, or gradually through its depth. All right? And again, the section is either fully elastic or fully yielded. Another important thing about these plastic hinge models is the only place the plastic hinges can form are at the ends of elements. So you've got to keep that in mind. If you don't know where the plastic hinge is going to form somewhere along the beam, you may need to use many elements to represent the beam, so you actually get the plastic hinge occurring at the correct place. This model is in this program that I'll be telling you more about, called Mastan, and I just wanted to provide you the website, but we'll talk more about that later. The other opportunity here is to use what's called a distributed plasticity model. Again, we're still using line elements, so it's not super complicated. This type of model is often called a plastic zone analysis, but it can actually capture yielding through the depth of the member, and it can capture yielding as it occurs along the length of the member. Unfortunately, to do that, it's having to numerically integrate the cross-section to get the element stiffness, and that's a bit time-consuming. And so it is more accurate, especially if you're looking at structures that only have 1 or 2 members in them. So you want a much more of a microscopic look at the behavior of a small system. But it is more accurate. But like I said, to do this numerical integration, it's computationally more expensive. It'll take your analysis time a bit longer to do. The other option we have is we could just simply do a full finite element analysis using shell elements, Abacus or Adena, ANSYS. But clearly this would be very expensive and quite slow if you wanted to look at an actual structure. In fact, probably impossible. So let's walk through a simple example. What I've got here is a W12 by 50. I'm going to assume that it's fully braced. So I just need to do a 2D analysis here. I've got a 100 kip load at 12 feet, another support at 12 feet, and finally out at the far end, 36 feet out there, I've got the final support. And modulus elasticity is 29,000, 50 KSI steel. So I would go into a program like Mastan, and I would prepare a computer model of it. And now what I'm going to do is gradually apply the load on the structure. And as I'm doing that, the program is constantly monitoring, as it's gradually applying the load, has anything yielded? Have we achieved a plastic hinge anywhere? And in this case, you can see that I've run the load up to 83%, 0.83, And on the left end of the member here, we've got an actual plastic hinge form. So the moment on that left end equaled the plastic moment capacity, and Mastan would say, okay, we're going to put in a plastic hinge here, and this member cannot take on any additional moment at this place. So it's going to zero out its stiffness for any additional loading. It can still support MSOP, it just can't support any more. Then what will happen now is eventually we put on more load. Again, we don't have a mechanism. The structure was indeterminate, and it's still indeterminate. But eventually what we'll hit is a second plastic hinge. So now out at the midspan of that first area, we've got a plastic hinge forming at about 89% of that 100 kip load. Again, the structure is still stable. It can take on more load, but it's had a remarkable hit with respect to its stiffness. And then finally, if we keep putting on load right at the 100 kips, 99.9% of it, I get another plastic hinge to form. And at this point, I have what's called a mechanism, and this beam is done. It's lost all of its stiffness. So if you have a look at this force displacement response curve, and so I created this within Mastan, on the horizontal axis what I was plotting was the midspan deflection, so where the applied force with vertical midspan deflection. And on the vertical axis I'm plotting that applied load. And what you can see is each one of these dots indicates sort of a load increment, and I'm putting more and more load on, and then suddenly right around here, like I said, about 83% of the load, I got that first plastic hinge, and when I did, I had a loss in stiffness. At 88%, I got that second plastic hinge, and now I've had a significant loss in stiffness, and then I keep coming across until I finally got that third plastic hinge. Now I have a mechanism, and there's nothing resisting anything in the midspan, and we've got unbounded deflections. Now, once again, axial force is not your friend when it arrives to the party. So here we're taking a look at the inelastic behavior of a beam column. So up at the right end, I've got both axial force and bending on there. And what I wanted to do is just show you what happens to the moment rotation response when axial force arrives. The first thing that you'll notice is that the stress diagram is no longer nice and happy with MC over I, but we have to shift it by P over A. So we've got larger stresses in this case at the top and smaller stresses down at the bottom, and our elastic neutral axis has been shifted away from the centroid. No problem. We do have a good bending stiffness of 4 EI over L, and we keep applying that axial load and bending moment, and what's going to eventually happen is once again we'll form a plastic hinge. But the important thing, at least I'm trying to show you here, is that plastic hinge will form. Again, we'll get full yielding throughout the cross-section, either in compression or in tension. But this occurred at a moment which was significantly less than the moment that it took before to get that plastic hinge. And that reduction is because axial force is now present. Again, for something like this or a program like Mastan, to simplify things, we'll ignore that in-between, and we'll just call the section either fully elastic or fully plastic. Now, one of the things that we can do is we can take the stress distribution and we can actually resolve it into two parts. The first part would be that's which the moment term would be have been creating, and because we need moment, we need a balance between the compressive stress and the tensile stress. So it's pretty easy to pull out the moment portion, and you can see that that moment portion is indeed less than M sub P. The other portion that's in there is the axial force portion, and that is certainly less than P sub Y. And so we have, again, a fully yielded section, and it's occurring when the ratio of M over MP is less than 1 and the ratio of P over PY is less than 1. So what we can do then is we can have a look at all the different possibilities of axial force and bending. So again, if you have a look at these axes, I've normalized the horizontal axis. It's representing bending divided by M sub P, and the vertical axis is the axial force divided by P sub Y. If we just go vertical here, that was the very first case I looked at of an axial force member, no bending, and we can get all the way up to P sub Y. On the other hand, our second case we looked at was all bending, no axial force, and when we do that, we can get all the way out to m sub p. However, on the last slide I was showing you combinations, and as a result of these combinations, we can't fully achieve either m sub p or p sub y. So what we could actually do is plot up all the different possible scenarios, lots of axial force, small amount of bending, whatever you want, and what you would end up with is something called a yield surface. So what a yield surface represents is sort of the interaction between axial force and bending, of which when you have your forces reach the yield surface, that's when a plastic hinge would form. If your axial force and bending moment for the member are within this yield surface, the member is elastic. If it hits the yield surface, we need to zero that stiffness and call it yielded or plastic. So now one of the things about this yield surface is a program like MassDen won't let you get outside of the yield surface. It will actually constrain the movement. So if you get some yielding, what can happen is the program can take on additional axial force, but it would have to redistribute bending moment to do that. And that's what you can sort of see happening in this slide. We reached the yield surface. This particular member wanted, or section wanted to take on more axial force, but to do so, it had to redistribute bending moment to its neighbors, and then it could take on more axial force. But in no case is it allowed to be outside the yield surface. So what's a material nonlinear analysis look like? Well, the first thing it's going to do is exactly what we learned last week, the direct stiffness method, but it's going to not put all the load on at once. It's going to put the load on in increments. And so for each increment of loading, it's going to solve for an increment of displacement. Now this is the structural stiffness being represented here, and what's happening during the analysis is during each load increment, the program is checking to see if any of the cross-sections have reached the yield surface, that is, have there been any plastic hinges. If there have been, then the load step is scaled back so that right at the end of the load step, a plastic hinge would form. How it's doing that then in the next step is it's going to say, all right, we've got some yielded members in our structure, and what it does is it looks at the elastic stiffness of those members, and then it reduces the stiffness of those members by what we call a plastic reduction. So it reduces the stiffness, and even though I show a plus sign, that would be a negative number, and so we reduce the stiffness, and we're reflecting the fact that the structure has yielded. What we would do at the end of the step then is we would add the increment of displacements and the increment of member end forces that we got to the total from the previous step, and then we would start on and run another increment of loading. So again, it's an incremental analysis where you're doing increments of loads, calculating increments of displacements, and for each increment, it's reflecting the yielded scenario of the structure. So let's return then to our example, but this time I just wanted to show you what happens when axial force comes on. So it's the same beam as before, but I've added 400 kips of axial force. So here we go, a first order inelastic analysis, and we've got axial force on there and that vertical force on there at mid-span. And you can see the plastic hinges have formed. At about 65% of the load, you get the first plastic hinge to form. Structure's not dead. It keeps taking additional load. So we keep increasing both the axial force and this gravity load of vertical force. Eventually we'll get a second plastic hinge to form at 67.7% of the load. It's still not a mechanism. It can take more load. And eventually at 73% of the load, we finally get a mechanism and we've fully yielded the beam. Now if you compare this against what I was showing you earlier in slide 23, for the case when there was no axial force, you can see that the axial force really reduced the load increment, or the proportion of load at which a plastic hinge would form. The first plastic hinge was previously without axial force. It was forming at about 83% of the load, and now it's forming about 65% of the load. The ultimate load, before I could get all the way up to 100 kips on there, now I can only get about 73 kips there in a proportional amount of compressive force before I fully yield the member. So axial force will have an impact on the strength. Here is again the same response curve. Whoop. Let's see, I jumped ahead. Sorry about that. So here again is the response curve I was showing you before, and mid-span deflection versus the applied vertical load. And you can see that without the compressive load, things were pretty good. I was able to get all the way up to the full 100 kips, include compressive load, and I'm getting those plastic hinges to form. Again, a loss in stiffness in that central span, and finally a full mechanism, again around 73% of the load. And when we have a full mechanism, the structure has no stiffness, and we have unbounded deflections. I thought you might find this slide kind of interesting. This is showing you the yield surface that's actually in masthead. Again, on the horizontal axis, we're monitoring at each one of those cross-sections the bending moment normalized by the plastic moment capacity. And on the vertical axis, we're monitoring the axial force divided by the yield load, or P sub y. And the yellow curve here is the response where the first plastic hinge forms. So it looks like I was putting the loads on in about 10% increments, and at about 6.5 of these increments, the forces at that cross-section reached the yield surface, and we got a plastic hinge. Now if we count 6 increments on the right side of the beam, we're about here. So we don't have a plastic hinge at 65% of the loading, but what's going to happen is we are going to get that plastic hinge forming at the left side, dramatic loss in stiffness in the structure, and we start immediately seeing this cross-section over on the right side dash off and hit almost 2 load steps later right against the yield surface. So I think, Brent, I'll stop there and see if you have any questions for me.
Sure, Ron. We've got a couple questions, but before we do that, we have had a handful of chats regarding your audio level.
Okay.
And I want to try to adjust that real quick. It's coming. I guess the comment is it's coming back a little heavy and fuzzy. So
okay.
Try to adjust your headset just away from your mouth just a little bit.
All right. How about that? Any better?
Can you say a little more, please?
Sure. Deflected shape, first order inelastic analysis.
Okay. I'm finding that as an improvement. If anyone feels they'd like to chime in with the chat, go ahead, but I think we do have an improvement there.
Okay. I'll give it a try then. I think I may have been too excited at the beginning too. So I was probably yelling.
Hey, we were all excited, Ron. So let's do a couple questions and we'll keep moving ahead.
Okay.
So here's the first question. Can you have a true plastic hinge if the member is non-compact or slender with respect to flexure?
Yeah, very, very important question. So when we start going with this material nonlinear analysis, we've got to make sure that our cross-sections are compact, that they can fully yield, and not only can they fully yield, they can undergo a significant amount of rotation before they will reach that limit state of local buckling or whatever the attendee was asking about. So it is very important when we do an analysis like I'm showing you that the cross-section itself is stocky enough to undergo those large deformations. And the defining element is, again, assuring it meets AISC's compactness requirements.
Okay. And then can you go to slide 23 for me, please?
Okay. Yep.
Okay. Question regarding slide 23. Why does the program insert the plastic hinge at a load ratio of 0.83 rather than when it equals 1.0?
Okay. So what was happening is, first of all, the program puts on the loads in increments. So let's suppose it's putting it on in 10% increments. All right. So it put on 10%, then 20%, and at each end of this, 30%, it goes and it evaluates the structure to see if it has any full yielding anywhere. Nope. All right, now let's go to 40%. Any yielding? Nope. Eventually it got to 80%. It still had no yielding anywhere. And then when it went to go to 90%, what it found is midstream in that load step, a plastic hinge would have formed at that left end. So the program automatically scales back the load step, so it's only 83% of the load. It figures out when it would occur, and then it puts in the plastic hinge, and then you start moving from there. So it put in the 83%, it put in that plastic hinge. Then the program tried to take another 10% jump, go to 93, but in doing so it found, oh wait, a plastic hinge is going to form within this load step, and it scaled it back so that it looks like around 88, 89% of the load, another plastic hinge would form. So it scaled back the load step to capture that plastic hinge and reflect now, two plastic hinge, a fairly heavily yielded state of the structure, and then it moved on from there. So I think that should answer that question.
Okay. And then let's go to 29.
All right.
All right, and then go ahead and go through the animation so we have everything up. But the question is this: did the program include P.delta effects as part of the analysis?
Oh boy, that's where we're going next. So no, right now what we have is an ice cream cone, but it hasn't been dipped yet. So no, we're on first order. All right, and you can see in both of the computer screens it's reading first order inelastic. Those P.delta effects are going to come to life when we start to account for them or run what's called a second order inelastic analysis. But before doing that, I think I need to take off and let's introduce just the topic of second order elastic analysis, and then I'll come back and look at this second order inelastic as the attendee is asking about.
Okay, and then let's do one more question. Go to slide 30, please. And the question is asking to clarify, did you say that a plastic hinge didn't form until 0.4/hinge 3? If so, can you please review that? I'm having trouble understanding.
Okay, let's see. Let's just sort of replay the slide. On the horizontal axis, in this sort of where you can see the yield surface, what I'm plotting there is we're monitoring the bending moment divided by the plastic moment capacity, and we're also monitoring at that same cross-section the axial force normalized by the yield load in the member, P sub y. So each one of these dots down here represents, each one of these curves represents what's going on at a different cross-section. All right, so the yellow curve is representing what's going on over on the left side of the beam here. So each one of these points is showing you the combination of bending moment and axial force at that point of the analysis. So it looks like using the yellow curve, we went 10, 20, 30, 40, 50, 60%, and then when it went to go from 60% to 70%, that cross-section would have cut through the yield surface. The program said, no way, we're not going to let that happen, so it scaled back the load step to 65%, and then that cross-section yielded. If you're having a look at a different cross-section, for example, the right side of the member here, over at the right end, that's what curve blue is showing, and you can see that when that plastic hinge and very quickly after the next one forms, that cross-section suddenly started taking on a whole bunch of bending moment. And the reason it had to do that is the rest of the structure, those other first two plastic hinges, had deemed that sort of half of the structure as not being any good in resisting bending moment. So any additional bending moment was then being resisted by this cross-section on the right, and it immediately led to a plastic hinge forming there at around 73% of the load.
All right, and with that, let's move on to the next section.
Let's see. Oh, that's where we are. Okay, so second order effects. Well, the first thing is you'll often hear it called second order effects. You'll often hear it called P-delta, P-cap delta, and P-small delta. It's often also called geometric nonlinear behavior. So we can talk about material nonlinear behavior, that was the yielding, and the geometric nonlinear behavior being changes in geometry contributing to second order effects and a nonlinear response. Equilibrium equations. Well, the reality of the situation is that when you and I write our equilibrium equations, starting right from freshman year when we took statics, we should have been writing them on the deformed shape of the structure. All right? But quite conveniently, that first-year engineering professor doesn't do that. They always show equilibrium on the undeformed shape. And the reason for that is it would be difficult for the faculty member to have the students be able to actually pull this off, because in order to formulate equilibrium on the deformed shape, which is, of course, reality, they would need to know the deformations. But in order to know the deformations, they need to know the member forces. But to know the member forces, they need to do equilibrium on the deformed shape. So they have sort of a circular problem here, or what we might call a chicken and the egg problem. Now the remedy to this is what we actually do is we put the loads on again in a series of small increments or iterations, and after we put on the load or each small increment of it, we iterate, we keep updating the geometry until those deformations are consistent with the equilibrium. In other words, we do the loads in small increments, iterating each time so that we are satisfying equilibrium on the deformed shape. All right, so that's kind of a crux of the matter of these second-order programs. So what do we mean by equilibrium equations on the undeformed versus the deformed shape? On the left side, I've got a small truss here, and I think you can see that this diagonal member, the force in it is only being produced by the horizontal force H. The axial force P comes straight down and into the vertical member. That is if we formulate equilibrium on the undeformed shape. If we come over here and actually formulate equilibrium on the deformed shape, well, what would happen? Well, because of that horizontal force, that point up at the top would actually move over to the right some amount delta. And now this is sort of an interesting scenario. This diagonal member, which before was, when we formulated on the undeformed shape, it was only seeing force by H. Now that diagonal member is not only seeing force by H, but it's also developing force due to the fact that P times that displacement delta is producing an overturning moment, and that's needing to be resisted by the diagonal member itself. Now, so we will get different reactions, and we will get different member forces. Now, I feel a little cheap telling you this story about a truss, because trusses are often very stiff and not as susceptible to second-order effects. But you could certainly imagine a tall, slender truss, and in that case it would be susceptible to second-order effects. So I wouldn't want anyone to say, oh, trusses, I never need to think second-order effects. It's not true. It all has to do with the slenderness of your truss. All right, let's move to something a little more normal. Let's say some type of a beam column. So here I've taken the most simple case of all, and I've got a cantilevered column. I've got horizontal force on it, and I've got axial force. And if I formulate my equations of equilibrium on the undeformed shape, the moment diagram that I would actually get is shown here as the maximum moment down at the base is H times L, and it would just be linear in between. But if we another important point is if we actually monitor the displacement, okay, the horizontal displacement of this point versus the applied horizontal load, the stiffness of this structure, as we know, would be, the lateral stiffness would be 3EI over L cubed. All right? But things kind of change up pretty quickly if we actually face reality and formulate our equilibrium on the deformed shape. So now I've got my free body diagram, if you will, over here on the right, and I'm going to do equilibrium on the deformed shape. So of course I've still got the moment down at the base being H times L, but I've also got an overturning moment, P times delta, that is adding on top of that, H times L. So the total moment at the bottom is actually larger. It's HL plus P delta. And of course this varies. The deflection is not linear. So the P delta effect does get smaller as we get towards the top of the structure, but it's certainly not going to get smaller in a linear fashion. So it's a certainly a more complicated situation. Very important to tonight is that if we take a look at the lateral stiffness of our simple system here, that is, again, we're monitoring lateral deflection versus applied horizontal load. Over on the left, it was very easily 3EI over L cubed. But we've invited compressive axial force to the party, and this is the type of response we'll get. And what we'll see now is that the effective lateral stiffness is actually less than what we might call the first order stiffness, or 3EI over L cubed. So again, that axial force is producing trouble, and it's reducing our lateral stiffness. All right, so there we go. Effective lateral stiffness is being reduced as a result of formulating equilibrium on the deformed shape. Now let's move to a slightly simpler problem, one that we can actually put at least some equations to and get our head around. What I've done here is I've just taken an axial force member, just a typical truss member, and up at the top I've connected a lateral spring to it. All right, and what we're going to do is just look at the response of this structure when we apply a horizontal and axial force. And again, I'm going to focus here on doing this response, formulating equilibrium on the undeformed shape. All right, so really by formulating equilibrium on the undeformed shape, pretty straightforward. We apply a horizontal load. The only thing that's resisting deflection is the spring itself. There is no overturning effect due to the P-delta effect because we're doing equilibrium on the undeformed shape. And so the lateral response of our structure, again, plotting lateral displacement versus applied lateral load, is quite simply the lateral, this slope, this curve here in green, a nice straight line, and that lateral stiffness, or the slope of that green line, is simply the stiffness of the spring. All right, so that's easy math to do. Unfortunately, again, it's not correct because we have formulated equilibrium on the undeformed shape. So let's approach this same problem again, but this time we'll formulate it on the deformed shape. All right, so same axial strut, same spring. We come over, and now we're actually going to do the equilibrium on the undeformed shape. And when we do this, what's going to happen if we were to plot the lateral response versus the applied horizontal force, before the lateral stiffness was just that of the spring, but now what's happening here is the effective lateral stiffness is being reduced. All right? This P-delta effect is producing more force in the spring, more displacement in it. So what's happening here is we're getting a nonlinear response, and the effective lateral stiffness is certainly less than it would be of just K for the spring. So let's go a little bit further with some numbers here. So here I've set things up. I've got a very simple free body diagram, if you will. We're having a look at the forces, the applied forces, of course the horizontal force and the axial force. We'll assume that we've got some amount of deflection, and we're going to formulate equilibrium on the deformed shape. All right. The resistance to the overturning is being produced by this reaction, R. And that reaction, R, we can actually calculate is the product of the spring stiffness and the displacement. So F equals KD. So the reaction is equal to the K of the spring times delta. So we'll keep things simple. Let's assume the deflections aren't very large. So the diagonal height, this length and this length are approximately the same. So the deflection isn't too large. If we sum moments down across the bottom, so down up across point P, we know the sum of the moments have to be 0. So acting in a counterclockwise direction, we've got R times L, so the reaction times L, the height. And acting in a counterclockwise, so the first one is in a counterclockwise direction. Acting in a clockwise direction is a moment H times L, and that overturning moment P times delta. The next piece of math I did is I simply divided both sides by L. Now I'm going to do a substitution. As I said before, the reaction is proportional or is equal to the spring stiffness times the deflection. So I'm just going to do a substitution there for the reaction. The right-hand side had stayed the same. And then what I'm going to actually do is solve for H. All right, so we solve for H, so we're going to subtract over P delta over L. And then I'm going to just collect some terms. And what I'm left with then is the effective lateral stiffness of the system. So again, we were making that plot, and it's no longer just nice and happy K spring, but the effective lateral stiffness is being reduced because of the presence of this axial force. All right, and the amount it's being reduced in our very simple problem is P over L. All right. So this is a kind of a real simple example that you'll want to take another look at after lecture and just follow through the math. It's not rocket science and certainly something you can do. This form, though, is pretty important to us. So some thoughts. Well, first, the deflections, I assume they were small. clearly this whole math starts to get a little crunchy if the deflection divided by the length of the member is more than 1 in 5. That's probably very unlikely for civil engineering structures, but if that were to happen, no problem. Instead of doing the load all in one step, we'll just put the load on gradually in several steps. So we can solve that problem. And like I said, for most civil engineering structures, the deflections are certainly much less. They're often limited by serviceability requirements, so they're most likely that delta over L would be less than 1 in 400, never mind 1 in 5. But again, what I wanted to show you here with this very simple example is that lateral stiffness is what we might call the first order stiffness, that of the spring, and where it's being reduced due to the presence of that axial force, P over L. So here's the first kind of time I'm showing this in general form, is that the second order stiffness is equal to what we call the first order stiffness, EA over L, the K of the spring, for EI over L, whatever the expression was we were looking at, being modified by a geometric stiffness term. All right? And that geometric stiffness term, for the very simple example we just did, is P over L. And the geometric stiffness term, I show it as a plus here, but if the member is in compression, it will be a negative amount. So let's have just a brief discussion about geometric stiffness and maybe put it in something that you can appreciate more. So we're talking about the effective lateral stiffness of a member. All right? So let's suppose you're the structure and you're out hiking, all right? And you come to a rest point and you take off your 50-pound backpack, okay? And what I want to show you is what happens as a result of putting that backpack on, okay, putting it back on. And what's going to happen here is if you don't have your backpack on and your buddy comes up and he pushes you on the shoulder, you have quite a bit of stiffness to resist and push back, and you're not falling over, you're quite happy. But if you come over now and take that backpack and put it on, 50 pounds, now your buddy comes up and pushes you, you almost fall over immediately. All right? So you've completely lost your lateral stiffness in pushing back against your buddy as a result of this compressive load. All right? So the effective lateral stiffness of structural members are decreased as a result of putting them in compression. Now, I know the question you're asking, and that is, well, what happens if the member is in tension? And the truth be told, it's kind of cool. The actual member increases its lateral stiffness. All right? So this is a good thing. So our geometric stiffness would not be negative as it is for compression, but it would actually be a positive amount. And so this is good news. And the example there that's often used is a guitar string. When you pluck a guitar string, it vibrates at a certain resonance, and you hear a certain sound. And then when you tighten the guitar string, you haven't changed its mass, but you have significantly changed its stiffness as a result of that tensile force. And as a result of doing that, when you pluck it, it vibrates at a higher harmonic, or whatever the correct word is there, and you've sort of changed the stiffness of that spring by increasing its tension. So that's how this program, MASTAN, works. In several programs, Strand 7, and several other programs out in the commercial world. But there are other programs and other ways for accounting for second-order effects. Again, computational, well-defined, and they use stability functions. And honestly, they're just as good, and especially for the civil engineering structures we look at, both geometric stiffness matrix approach and stability function approaches will give the same answer. All right, so let's go back to real members and not backpacks and guitar strings. Let's have a look at flexural members. So on the left is one scenario I've been showing you, bending of a member subject to axial force. On the right, we're putting on a shear force and getting bending. As we were saying last lecture, in both cases, okay, the stiffness of these members were a function of the geometry, which included the moment of inertia and the length of the member. Increase the moment of inertia, you're going to increase the stiffness of the member. Increase its length, you're going to decrease its stiffness. We also looked at the material and said, all right, what's representing the material stiffness of that member? It's its elastic modulus. If you increase the E value, you increase the bending stiffness of the member. But now there's a new player here, and that's axial force. And as I was showing you before, the axial force, if it's in compression, it's actually going to reduce the bending resistance of these two members. All right, so if we think of the member on the left as some type of a rotational spring, during the last lecture we said, well, that stiffness in that bending member is a function of its moment of inertia, its length, and its material modulus. Well, now it's also a function of the axial force in the member. Likewise, the shear bending stiffness is a function of moment of inertia, length, and E, but also the axial force in the member. So I think the next slide, yeah. So here I've actually gone on and just put some numbers to this. For this particular example, as we were showing last lecture, the flexural stiffness is 4EI/L, but when you include axial force and include second-order effects, we've reduced the flexural stiffness from 4EI/L to 2PL. We reduced it by 2PL/15. So if the load's in compression, it's a negative sign there. I think we showed this example last week as well, putting some numbers to it. The flexural stiffness here is 12 EI/L cubed, looking at the beam on the right. And again, we put axial force on there. We don't have 12 EI/L cubed anymore. It's being reduced by 6P/5L. Again, just showing these, not expecting you to memorize them or anything like that, but the key here is that when we do a second-order analysis, we're taking the first-order stiffness and we're reducing it by some type of a geometric stiffness, and that geometric stiffness accounts for the presence of axial force. And that, in turn, will give us our second-order stiffness. So how do we actually run a geometric nonlinear analysis? Very similar to how we did the material nonlinear analysis. We'll put the loads on in increments. All right, so we're going to put on an increment of loading. We'll formulate the stiffness of the structure, and for that increment of loading, we'll solve for the increment of displacements. At the start of each load step, we'll evaluate the structure. We'll take a look at those member forces, and we'll use those member forces, the axial forces anyway, to calculate geometric stiffness terms. Those geometric stiffness terms then will reduce the elastic stiffness terms, just like I was showing you on that previous slide, and that will actually represent then the stiffness of the members. We'll then take the load step with the second-order effects included in the analysis, and a very important step here is at the end of the increment, now the members, let's say, are not as vertical as they were before. Those columns now have a little bit more lean in them. Before we take the next load step, we actually update the geometry of the structure. So that's how we can include both the P cap delta effect and the P small delta effect by not only using the geometric stiffness terms, but also updating the geometry as we gradually apply the load. At the end of the load step, we would take the increment of displacements that we have. We would add it to the total that we've got up to this load step, and that will give us the total deflections in the structure. Likewise, we would get an increment of element N forces. We would add them to the total element N forces up to this point in the load history, and that would give us the total element N forces on the structure. And we could keep applying more and more load, and either the structure is going to be quite happy. If it's an elastic analysis, we could actually at some point compute an elastic instability. And there what's happening, and we'll take a look at this a little bit more at the end of the lecture, is these geometric stiffness terms have actually reduced the elastic stiffness to the point in which the structure buckles. And so that's kind of neat. So we can actually pick up an elastic instability from this type of model. This is just showing you some mass tan results, not very dramatic. Up at the top, here's our example that we've been looking at. Again, I've got a vertical force and an axial force. This axial force is causing trouble because it's producing compression in the members. The compression in the members are producing a negative geometric stiffness term, and it's reducing our first-order elastic stiffness. We can see that down in the response curve here. On the horizontal axis is the mid-span deflection at the applied load. The vertical axis is the applied vertical load. For a first-order elastic analysis, everything is linear as we'd expect. For this example, I've put the loads on in 10% increments, and I've monitored, well, what's the displacement at that load at each one of the increments. And you can see by the time I get all the load on there, not a big difference between the first-order results and second-order results. But even though that response curve, they look pretty similar, it is more interesting when you actually plot the moments out. All right. So I've got two moment diagrams here, results of two different analyses. The top one included second order effects. Both moment diagrams are from elastic analysis, so I haven't accounted for any yielding. Like I said, the top one accounts for second order effects where the bottom one doesn't. And if you take a look at these moment diagrams, what you can see is that they differ by about 10%. And the truth be told, the second order analysis, the moments are being increased by about 10%. All right? And so it's not a huge amount, but it is defined as enough that we want you to include that when you design structures. So we are saying that second order effects need to be considered, and this is why the moments could be bumped up by as much as 10% for this very simple example. They may be more for your structure if it's a very flexible structure, or they may be less if it's a very stiff structure. So you can't just make one statement to cover all of them. You actually need to do the analysis. Okay. The next step then is what the attendee was asking about, and that is they wanted the full enchilada. They didn't want just second order. They didn't want just inelastic. They want a second order inelastic. And so this is really fun because now you're not only doing equilibrium on the deformed shape, but that deformed shape also includes any yielding that could have taken place. All right. Well, guess what? We're going to use the same method that we've used all along. All right. So we're still going to use this direct stiffness method. Again, we're going to put the loads on in load increments. And for each load increment, we'll calculate an increment of deflections at all the points. But the stiffness now in the structure is going to be reflected by not only the elastic stiffness, not only the yielding, that would be reducing the stiffness, but also the second order effects will be reducing the stiffness. All right. So at the start of each increment, when the structure, when we go to define the stiffness of the members, what we're going to do is for each member, we'll start with its elastic stiffness. We'll have a look at how much axial force is in the member. If it's compressing, we're going to reduce it. If it's tension, we're going to increase it. So most likely, let's say compression. So we reduce the elastic stiffness to account for the geometric effects. If the member is yielded or yielding, then we'll reduce it even further to account for the inelasticity. So that's how we basically get to the stiffness for each member. Then we would take the load step, and at the end of the increment, again, very important that we're going to update the geometry. And this is, like I said, important because once we have yielding involved, our deflections often get pretty big pretty quickly, and there we really do need to be updating that geometry. And we'll continue to do this. So for each load increment, like I said, we'll calculate an increment of deflections. We'll add that to the total that we've got up to date, and that will give us the total at this point of the analysis. For each, again, increment of loading, we'll calculate the increment of displacements. From those, we'll calculate the increment of element end forces. We'll add them to what we had from the previous load step, and that will give us the total element end forces. And we'll keep applying this until our structure either gets in a very yielded state or, in fact, an inelastic instability is achieved. So here we are back at mass 10, and we've cranked it up one notch higher. We're not only doing inelastic as we were before, but we're also doing second order. And so the second order effects, this is when the plastic hinges would form. I brought back the slide from before. That was slide 29 that showed when the axial force was on there. So in both cases here, we do have axial force. But when the axial force was on there, but we didn't account for second order effects, the first plastic hinge didn't form until 65% of the loading, where here it's forming at 63%. Not a big deal. But what's kind of interesting, so when the first plastic hinge forms is, just a very small difference. But once we start getting plastic hinges to form a second one in the center, then the deflections start to get larger. And when the deflections start to get larger, the second order effects become more significant. And we actually achieve up at the top here the full plastic mechanism at 67% of the loading, as opposed to before when we weren't accounting for those second order effects, the limit state was at 73% of the loading. All right, so the second order effects in this example do, again, reduce it by a number of about 10%, reduce the strength. Well, now we're really getting quite exciting with our response curves. We've got them all shown here. Again, mid-span deflection versus applied vertical load. And we've gone from second order elastic, then we went first order inelastic, but no axial force. Then we included the axial force but no second order effects. And then when we got everything in the picture as it's being shown here in this magenta color curve, we've got second order effects and we have inelasticity. And that's pretty much the best representation we're going to get at the limit state response of this system. So I think, Brent, this is another good stopping place for some quick questions. I am running a bit behind, but can take certainly 2 here.
Okay, Ron. Yeah, let's try to do a couple questions, and we'll move on. Looking at slide 38, the question is this. Based on slide 38, is this why in X-brace systems we can use a tension member to brace a compression member out of plane?
Yep, this is the exact reason for that. Perfect question.
And then, so adding on to that, then how much tension is needed to significantly enhance that stiffness from the tension? You know, that's a good question. I don't know of any ad hoc equations. Maybe we'll have to answer that question if we can find some quick information. But off the top of my head, I can see the effect that's happening. The tension member is more or less bracing that compressive diagonal at midspan, usually where they cross. But how much tension is actually needed to do that? I actually couldn't give you a number. You know, I think it's a fun example to run out on your computer program and actually see this take place. But in most cases, I believe this, even in the commentary now, in the 2016 commentary, we're going to include some sentences granting one permission to do that. And I don't think the commentary has any limits. I think if you have a small amount of tension, then most likely you have a small amount of compression. And if you have enough compression to buckle the member, the diagonal compression member, and then mostly the other diagonal, which is in tension, is going to have enough tension force to develop that effective length that you're trying to use. Okay, and let's go to slide 41 real quick. We had a couple of questions about this incremental loading.
Yep.
In your example, you used a 10% increment. And so the question is this typical to do the load steps in 10% increments? That's the first question. And then the follow-up is how much does the load step increment affect the final results of the analysis? Yeah,
these are perfect questions. I'll probably forget them. So let me answer the second one first, but you might need to remind me of the first question. So the second question is how many increments do I need? All right. Well, any time you go to a nonlinear analysis program, my best advice to you is you actually need to do what's called an H convergence. And that is you run it for 10 steps, you get your answer, and then you say something to the effect, all right, what would happen if I cut the increment in half and use 20 steps? And so then you run it for 20 steps, and you'll find that the change was nothing. There was a small change, 1% or something like that, and you conclude that you've made the step size small enough so that you're good to go. All right. So that's one way to get there. And the other thing that most of these programs are doing, and it's again, you're not even touching it, you're just watching it in action, is they're doing it iteratively. All right. So they're putting either some of the load on or all the load on, and they keep iterating on that load until they get equilibrium. And then it's not until that point in which the program then stops and tells you that, yep, we've got there, this is the solution. And so the programs that include an iterative solver are real nice. It's sort of like getting a car that's turbocharged or whatever. They are real nice because their solver is going to keep iterating until equilibrium is in fact defined on the deformed shape. And so you don't need to worry about then the size of the load step.
Okay, let's go where we left off. We finished 45. Let's go to 46 and take it to the end.
All right. Well, not a lot left here, but certainly a good 10 minutes worth of work. I'll move it a little bit faster. But the last one is we looked at a material nonlinear analysis. Then we looked at a second order analysis. There is one more type of analysis that comes with most programs, and it's called a critical load analysis. It's often called a buckling load analysis, or it's often called an eigenvalue analysis. And it's slightly different than your second order analysis. In your second order analysis, what you are doing is either iteratively or in increments, you're applying more and more load on the structure until you reached equilibrium under the given loads. A critical load analysis is going to take your given loads, and they're going to figure out how much a scale factor against those given loads before the structure would, let's say, elastically buckle. All right. So what you're going to get back is not, you're going to get back a load factor of how many times your current load could be put on there before the system would buckle. And you'll get a picture, you'll get a nice view of those buckled shapes, but you don't really have any history on how you got there. All right. And that's the nice thing about this incremental analysis, is you can see the structure becoming unstable and when it became unstable, how it got there. Another important feature of the critical load analysis is most of the programs, Mastan has a little twist on it, but most of them are only for elastic buckling. So there is no reduction either for inelasticity directly or even indirectly using a TAW factor or anything like that. So first, let's talk about buckling and what it means. First, I've taken this cantilevered column, I put an axial force on the top, and I started squishing it. And as you would imagine, for a while, the structural member just gets compressed. It gets shorter, and the structural member is quite happy, and life is going on. But eventually what will happen is we'll get enough load on the system that the structure has a choice. It can either continue to squish vertically, or it can fall over left or right. And it's going to go wherever its least energy is required. And to go any further vertically, usually it would take more energy. So the shorter way out, the easier way out is for the structure to fall left or right, just keel over. And when it does that, that of course is our buckled shape. So what we're looking for then is this situation in which we move from solution 1 to solution 2. How much load does it take for that to happen? All right. So how does a computer do this? Well, like I said, it's a critical load analysis. And what it's basically doing is recall that the elastic stiffness of the member was a function of the first order stiffness, which was a function of the area, the moment of inertia, the length, the modulus, the orientation, and also the geometric stiffness. Now that geometric stiffness term, as you'll note in my previous slide, is always proportional, directly proportional to the axial force in the member. All right? And so that's a key element. So now if we take a look at the stiffness of the entire structure, we could actually take the stiffness of the entire structure and we could break it into two parts. One, the stiffness being reflected by just the first order elastic stiffness, and then we could take all of these kg points and sum them all together, and we can get what's called the geometric stiffness of the structure. Now an important element is that the geometric stiffness of the structure is proportional to the applied force. In other words, each one of those members, the geometric stiffness was proportional to the axial force in the member. The axial force in the member is proportional to the the axial force in the member is proportional to the applied force. All right. So now we've got this term then, and it's directly, like I said, proportional to the applied force. So what that means is if we were to double the loading on the structure, we would double all the forces in the members, we would double all the k sub g's, and we would effectively double this term. So what we're looking for then is when does this stiffness sort of become unbounded? All right? So to the computer, what it's doing is it's going to define buckling occurs when it goes to solve your system of equilibrium equations, and this stiffness right here, which is a reflection of these two parts, doesn't provide a unique solution. It provides, for example, in that previous slide, not only axial deformation, but that flexural buckling we were saying. All right? So the second it can get more than one solution, it's knowing, okay, we must be buckling. And so it's doing that actually by looking at this stiffness matrix for the system and finding out where its mathematical determinant goes to 0. and that's how it's finding these buckled shapes and buckling load factors. All right. Maybe if I work through a pretty simple example here, you can get it without having to take any determinants or anything like that. So here what I've got is a beam in a column. They are rigidly connected. The beam, though, is also rigid, so it's not going to flex at all. The column has an area, a moment of inertia, a length, and of course a modulus plasticity. And what we're after is finding out what's the buckling load in this system. All right. So key stiffness terms, again, if we have a look at the vertical stiffness, that is, we're applying axial force, how much does the member move up and down? Well, that one's pretty straightforward. All right, the vertical stiffness would be the axial force P multiplied K, equaling K multiplied by the vertical deflection. However, the lateral stiffness is really the key one here. So the horizontal displacement is proportional to the horizontal force, and it's by this lateral stiffness. And you might recall a few slides ago we actually looked at this system turned on its side, and I said, well, for that beam subject to shear, the elastic stiffness was 12 EI over L cubed, and then we're reducing that due to the geometric stiffness term, which is 6P over 5L. So really what we're looking for is at what point does our lateral stiffness go to 0? So we can actually just solve for P in that picture. So how does the solution work? Well, what these programs do is they apply a reference load. So in our case, we would apply the axial force P here. And they do a first-order elastic analysis to find out what the forces and moments are throughout the structure. And then it starts to look for a load factor, okay, that we could scale this force distribution against, and we would degrade the system stiffness to the point in which it would buckle. All right. So keep in mind in our example here, the lateral stiffness was 12 EI over L cubed for the first order stiffness, and then we were reducing it by 6P over 5L. But what we've got here is a buckling load factor of lambda, let's say. So the buckling load would be lambda sub P. So at what point does the lateral stiffness go for 0? So we can solve for lambda sub P. If we do this little piece of very simple math, we would find out that lambda times P is equal to 10 EI over L squared. And if we actually take a look, okay, so the critical buckling load on our structure is lambda times P, and that's the P critical. And like I said, just solving that very simple equation, it's 10 EI over L squared. Well, if we roll up our sleeves and actually solve the differential equations, we know that we're going to get pi squared EI over L squared. Pi squared is 9.87. So the theoretical buckling load of our system is 9.87 EI over L squared. And using only one element, we're within, what, 13% or 3%? What is it? Yeah, 1.3% of the solution. So that's pretty impressive. And this is, again, how these computer programs are doing the buckling analysis. They're looking at the point in which the structural stiffness would actually degrade and permit buckling. So here was that example I was looking at. Just to show you, we could do an elastic buckling on this system. It's pretty boring. We would find that this system is very stiff. It would take about 9.5 times the load that we had on there, 9.5 times that 400 kips before we would actually elastically buckle the structure. Now, Mastan does have a feature that a lot of programs don't, and that's the ability to do an inelastic buckling analysis. And it's interesting, once you account for the inelasticity, the buckling load factor drops all the way down to 1.7. Now that, again, is still well above that when we were getting plastic hinges and everything, and that's because this type of a buckling analysis doesn't account for yielding due to bending. It only accounts for yielding due to axial force. But it does get you a lot closer to the answer than elastic critical load does. I think the biggest use I see for these type of programs of this is just people want to see what does the buckled shape look like. And from the buckled shape, they can start thinking about increasing its stiffness, and where to increase its stiffness, where you might provide the best place to provide bracing and the like. The other thing is that in a structure like this, if I have a very high buckling load ratio, it's often an indication that the second order effects aren't that significant. But even with 9.4, we were seeing second order effects on the order of 10%. So that's pretty significant for a buckling load ratio of 9.4. So some thoughts on critical load analysis for large systems. Again, you would first do the analysis for a reference load. Then you assemble the system's first order stiffness, the system's geometric stiffness matrix. You would then solve the math problem in which you're looking for the determinant of when does that stiffness go to 0, when is it singular, and that's what we call the eigenvalue problem. The eigenvalues from this problem would be the critical load buckling factors. The eigenvectors from this math fund would be the buckling modes. All right. An important thing to note usually with these programs like MassDan and the like is that you will get a more refined solution closer to the exact theoretical solution by using more elements to model the compression members. But in my work, and I think Don White's going to talk about this in a few weeks, often just using 2, 3, or 4 elements to model a structural member is certainly enough. All right, so where have we gone? Well, our basic introduction is complete. Where do I go from here? Well, for you folks, at least most of you who have not experimented with nonlinear analysis, it's sort of like when you had to learn how to drive. All right. Well, the first thing you should do is read the driver's manual. Right. So go back and have a look at the slides that were provided you in the last 2 lectures. There's quite a bit of information there, so reread it just like you would reread your driver's manual. But the next thing you're going to need if you were learning how to drive is you'd need a car. Now, you would never use your own car or your parents' car because you might wreck it, so of course you borrow your best friend's car. Well, it's the same thing, okay, on the nonlinear side. You need to get some nonlinear analysis software if you're going to learn how to perform nonlinear analysis. All right. Once you have that nonlinear analysis software, again, you need to work lots of examples to become proficient at it. Now, what I think you'll find is if you're like most structural engineers, these examples start to become addictive. They're actually fun to do. You're finally solving some really interesting problems that you've always wanted to solve, but you never had the analysis software to do it. And this is very similar to driving. You know, in order to learn how to drive, you eventually have to go for a drive. And it's very scary at first, and you'll run over a few mailboxes. Hopefully you won't run over any people. But eventually you figure out how to control the car. And then now you've got your confidence up. You've worked examples. You've compared it against textbook problems. You're getting the same thing. And now it is time for you to try it out if you want to apply it in analysis and actually nonlinear analysis and design. It's not NASCAR. It's not that sophisticated if you're learning how to drive, but it does require a person who knows what they're doing. All right, so there you are driving away. So acquiring nonlinear analysis software, certainly a lot of the commercial programs are starting to have more and more nonlinear analysis capabilities, especially second order. All right. I've been pitching or telling you tonight about the MassDan software. If you don't have access to your company's software or you don't have a nonlinear analysis software, I think I've found good luck over the past years with people learning how to use MassDan and getting up to speed with it. MassDan is educational software. It's available at no cost, and even now the textbook that has all the background that Bill McGuire, Dick Gallagher, and I wrote a number of years ago is now available also at no cost, providing you the nonlinear analysis background to the Pt.II software. So feel free to download it at that site and start trying to figure it out. We've moved through all these different levels of analysis from first order elastic right down to buckling. MassDan does use a yield surface, so if you're using some other type of program, you need to sort of understand what yield criteria is it using. All right, so we know if we take an actual structure and subject to a gravity load and a lateral force proportionally, and we monitor, let's say, the lateral displacement versus this applied load, we'll have a response curve in which the structure starts to yield, and eventually it reaches its limit state or ultimate strength, and then it can't take any additional loading. We've got now lots of different analysis methods to get there. The first was a first order elastic, which did not include any second order effects and no yielding. Then we could get our buckling analysis to start figuring out when is it going to buckle. But then we could do a second order analysis without any yielding, and that would tell us sort of when the elastic stability would occur. Then we could do an inelastic analysis but first order, so that would tell us when a plastic mechanism would occur. Or we can just roll up our sleeves and do the full-blown analysis, and that would be a second order and an inelastic analysis, and that would actually very closely approximate the true limit state response of the structure. All right. So now problems like this, I show these people this lecture, and then they get all excited. They can't wait to start working out some examples. So here's one for you, and you're free to run all the different levels of analysis. I can't help but look at the moment diagram down in the lower right here. First order moments versus second order moments. Look at the moments in this column. All right. The first order moments were on the order of 14 inch kips, nothing. The second order moment was 1831, a big jump. Why did that happen? So start playing with examples and sort of understand it. So summary and conclusions. Okay, so I provided you an introduction to nonlinear analysis over the last 2 lectures. We reviewed the direct stiffness method. Then we looked at material nonlinear analysis. We focused on an inelastic hinge method. Then we did a geometric nonlinear analysis, or second order. First we did it elastic. Then we upgraded it to also include inelastic behavior. And then at the end I briefly spoke about this other feature called a buckling analysis, eigenvalue analysis, which is calculating a critical load or buckling values and modes for you. All right, so again, how are these programs doing it? How are they including these nonlinear effects? The only way they can, and that's by modifying the member stiffness. All right. I tried to provide you a quick overview and the availability of Mastan, so give it a try. And so now it's time for you to take it for a spin. And one of the things that I included at the end of these notes is a whole bunch of examples for you. We'll look at examples next week, but there's a bunch more examples at the end of this attached in the notes to this lecture. And so feel free, once you've got Mastan downloaded, to see if you can recreate the results in some of those examples. All right. Now, next week, I'm going to have some more fun with you before I finally turn it over to Don to get serious and start looking at design situations. So we learned first, for me anyway, last week, what is the direct analysis method? Then we shifted over to looking at linear analysis. This week we went nonlinear. Now, once we provide people the textbook, we provided them the software. The next step was we wanted to provide them a whole bunch of modules for basically understanding structural stability by applying the nonlinear analysis. So next week we're going to have some fun with a virtual lab and check that out. So I'm sorry I've gone over a minute or so here, but I think I'll turn it back over to you, Brent, for some questions.
Okay, thank you, Ron. Let's try to address a couple questions before we wrap things up. I know we're running over on time, so we'll just hit a couple, and those that we don't get to, I'll follow up with you, Ron, after the session, and we'll work to get those addressed.
Great.
So question is on this last section, slide 52. So the question is, why does the accuracy increase with more elements? How do you decide how many elements to use?
All right. Well, first, I answer the second one, as I did before. How many elements to use? Usually, the recommendation we do is you take a simple problem, and for that particular piece of software, use 2 elements. Did you get the right answer? No, you're probably off by 3 or 4%. Use 3, 4, 5 elements, and you keep increasing the number of elements until your solution won't change. All right. So it's kind of that's what we're doing there. We're just using more and more elements until we know our solution is accurate. Now, 9 times out of 10, if it's a side sway type of instability, 2 elements are enough. If it's sort of like not a side sway, but a non-side sway type of instability where the column is going through some serious curves, you might need to use 4 elements with Mastan. But again, it's a function of the sophistication of the software you're using and who programmed it and what type of elements they're using. So you typically would start with 2, increase it until it's not making any difference. Why do you need more than 1 element? One of the things to keep thinking about is when programs like Mastan or something are developed, we use an elastic stiffness, and that elastic stiffness assumes sort of a deformed shape. And in our case, we use what's called cubic polynomials. All right, so we use cubic functions to represent the deflection along the length of the member. Now, if you have a buckling shape that's in a serious sine wave and it's very tight, you will not be able to represent it properly with just a single cubic polynomial. So you might need a few elements. So now you're sort of breaking it up, splicing together a few cubic polynomials to get sitting right on top of that sine wave, or sine and cosine wave that's the actual buckled shape. So that's why you might need a few elements to get there.
Okay, and then I'm sorry, I think it's the last slide. No, I'm sorry, slide 56, please.
Okay.
Can you get the full slide up?
Yeah.
Give that a second to load up. The question is this: the second order inelastic graph forces seem to go down from the peak value.
Right, right.
Can you please clarify why that is?
Yeah, that's basically the definition of an instability. So what's happened here is either even the actual or the program's results. We got to this point, and at that point the structure has sort of buckled. It's got lots of yielding. Second order effects are dominating. It's falling over, and the thought here is it's starting to fall over, and the only way you can keep it in equilibrium and freeze the analysis is if you were to take off load. All right? So you're still getting positive deflections and you're pulling load off, and that's sort of the definition of an instability. So a lot of times what you'll see is sort of an unloading that will take place once you've reached any form of an instability. And it's just basically it's going, and I don't care if you take load off, I'm still going to get more deflection. So I think that's about as quick an answer as I could give you.
Okay. I think we're probably out of time for any more questions, so I just want to say thank you again to Ron Zemian, and thank you all for joining us. Let's go over other pieces that come with that 8-session registration. Specifically, you have access to the recording as well as a quiz. We send out an email every week within 2 business days, Wednesday at the latest, that has that link to the quiz and link to the recording. I just want to recommend anyone that doesn't receive that, please contact us right away so we can resolve any issues as to why that may not be reaching you. We'll do our best to figure out what the problem is, but we want to make sure you get that information so that you can get access to the quiz and recording. So why do we send that out? That's an added benefit for having that 8-session package. The quiz, if you happen to miss the live session and you're still wanting to get PDHs, you have to take and pass the quiz in conjunction with that recording in order to receive PDHs. Further, we do give people the opportunity to earn an EEU, and to get that EEU, which recognizes the effort of fully participating in this course, you need to pass 7 of the 8 quizzes, so that'd be another reason to take it. But we also think it's important to reinforce what's being taught in this course, so we do encourage you to participate to the fullest that you can. But the bottom line, though, if you do attend that live session, you do not need to take the quiz in order to receive PDHs. Well, that concludes session 2. My thanks again to Ron Zemian. Next week will be session 3, same time, same place. And